This wasn't supposed to be possible. A spaceship the size of a city, carrying 100,000 people to the stars, powered by something so violent it could level nations. Yet in the 1950s, America's brightest minds weren't just dreaming about it, they were building it. Project Orion promised to shatter every limit we thought space travel had. No chemical rockets struggling to escape Earth's gravity. No decades-long journeys to distant worlds. Just pure nuclear fire, detonating behind a massive steel plate, hurling humanity toward Alpha Centauri in a mere 44 years. The plan was audacious. Bomb after bomb would explode beneath the spacecraft, each blast pushing it faster and farther than any machine had ever traveled. 4 explosions per second. 800 nuclear devices just to reach orbit. It sounds like madness, but the science was solid. The physics worked. The engineers knew it could fly, so why didn't it? And what would the universe look like today if we'd chosen nuclear pulse propulsion over the cautious chemical rockets that actually took us to the moon? The answer lies in a story of brilliant scientists, impossible dreams, and the moment when humanity had to choose between reaching for the stars and protecting the planet beneath their feet. This is Project Orion, the nuclear bomb-powered spaceship that almost changed everything. The dream began with destruction. In 1881, a Russian revolutionary named Nikolai Kibalchich sat in a prison cell, awaiting execution for his role in assassinating Tsar Alexander II. Most condemned men might spend their final days in prayer or despair. Kibalchich spent his sketching rockets. Not just any rockets, spacecraft powered by explosions. His drawings showed vehicles that could harness the raw power of detonations to push them through space. The authorities executed him before he could refine his ideas, but the seed was planted. Sometimes the most dangerous thoughts come from the most dangerous minds. Decades passed. The idea lay dormant through 2 world wars, waiting for the right moment to resurface. That moment came in 1947, when Polish physicist Stanislaw Ulam put pen to paper at Los Alamos. Ulam wasn't just any scientist, he was one of the architects of the hydrogen bomb. A man who understood nuclear fire better than almost anyone alive. Working alongside his colleague Frederick Rains, Ulam began calculating something extraordinary. What if nuclear weapons weren't just instruments of war? What if they could be instruments of exploration? The mathematics were staggering. Chemical rockets, the kind that would eventually carry Apollo astronauts to the moon, could push a spacecraft to about 3 kilometers per second. Nuclear explosions could deliver thousands of kilometers per second in a single blast. The difference wasn't just dramatic, it was revolutionary. Where chemical propulsion promised decades-long journeys to nearby planets, nuclear pulse propulsion whispered of trips to other star systems within a human lifetime. But mathematics on paper meant nothing without engineers willing to make it real. That's where Ted Taylor entered the story. Taylor was a theoretical physicist with a reputation for thinking impossibly big. He'd already designed some of the most powerful nuclear weapons in the American arsenal. Now he wanted to turn that destructive force into something creative. In 1958, he partnered with Freeman Dyson, a brilliant British physicist who'd spent years studying the deepest mysteries of the universe. Together, they convinced General Atomics in San Diego to fund the impossible. Project Orion was born from a simple but radical insight. Traditional rockets worked by containing explosions inside an engine, channeling that force through a nozzle. But containment was the problem. No material could withstand the temperatures and pressures of nuclear fire. So why try to contain it at all? Instead, Orion would detonate nuclear devices behind the spacecraft, using the explosion to push against a massive steel plate. The ship wouldn't need to survive the blast, it would ride it. The engineering was elegant in its brutality. Picture a spacecraft with a thick steel disc at its rear, connected to the main vessel through a system of shock absorbers. Nuclear bombs would be ejected from the center of this pusher plate, detonating at a precise distance behind the ship. Each explosion would vaporize a thin layer of the plate's surface, creating a directed plasma jet that would slam into the disk and drive the spacecraft forward. The shock absorbers would smooth out the violent impulse, transforming nuclear fury into steady acceleration. The numbers were intoxicating. A basic Orion ship, weighing 4,000 tons and carrying 8 astronauts plus 100 tons of cargo, would need 800 nuclear explosions to reach Earth orbit. Each bomb would yield about 0.15 kilotons, small by nuclear standards, but still more powerful than the largest conventional explosives. One detonation every second would carry the ship beyond the atmosphere and into the void between worlds. But Taylor and Dyson weren't thinking small. Their imaginations soared beyond simple orbital flights to something that bordered on science fiction. They envisioned the Super Orion, a spacecraft 400 meters in diameter, weighing 8 million tons. This wasn't just a ship, it was a flying city, designed to carry 100,000 people across the galaxy. The pusher plate alone would span 20 kilometers, made of materials that could withstand repeated nuclear bombardment. Some designs even suggested making the plate from uranium, so it could be cannibalized for fuel once the ship reached its destination. The physics supported these wild dreams. Conservative estimates suggested that a nuclear pulse spacecraft could reach 9 to 11% of the speed of light. At those velocities, the nearest star system would be just 4 decades away. Humanity wouldn't just be taking its first steps into space, it would be leaping across the cosmos in a single generation. Testing began immediately. The team couldn't use real nuclear weapons, so they substituted conventional explosives. In the California desert, they built a 1-meter test vehicle nicknamed Hot Rod. On November 14, 1959, Hot Rod lifted off powered by RDX explosives, climbing 184 feet in 23 seconds before parachuting back to Earth. It was crude, it was loud, and it was beautiful. For the first time in human history, a spacecraft had flown using external explosions. The tests revealed both promise and problems. The basic concept worked. Explosions could indeed propel a vehicle upward, but the engineering challenges were immense. The shock absorbers had to function perfectly with millisecond precision. A gap of just 10 milliseconds between explosions could tear the pusher plate clean off the ship. Loading and firing hundreds of nuclear devices required machinery that was part cannon, part vending machine. The team even consulted with Coca-Cola about the automated handling systems. More troubling was the issue of ablation. Each explosion would vaporize a thin layer of the pusher plate's surface. Over thousands of detonations, would the plate erode away entirely? Computer models suggested it wouldn't, but no one could be certain without testing hundreds of real nuclear devices. The team was designing a spacecraft that could only be properly tested by building and flying the actual thing. Then came an unexpected gift from the weapons testing program. During Operation Plum Bob in 1957, a nuclear test accidentally launched a 900-kilogram steel cap at tremendous velocity. Photographic evidence suggested it might have reached escape velocity, 6 times faster than needed to leave Earth's gravitational field. The cap was never found, presumably vaporized by atmospheric compression. But it proved that nuclear explosions could indeed accelerate massive objects to incredible speeds. The implications were staggering. If a simple steel cap could be blasted to escape velocity, what could a properly designed spacecraft achieve? The Orion team began calculating trajectories to Mars, Venus, and beyond. Freeman Dyson wrote with barely contained excitement about sending ships to other planets by 1968. The space race wasn't just about reaching the moon. It was about reaching everywhere. Yet, even as the engineering progressed, darker questions began to surface. What would happen to the planet below when hundreds of nuclear devices detonated in the atmosphere? how much radiation would rain down on the cities and farms beneath each launch. The bombs were small, but they were still nuclear weapons. Each Orion launch would be equivalent to a modest nuclear war. The team tried to minimize the impact. They designed the bombs to burn as cleanly as possible, reducing radioactive fallout. They calculated launch trajectories that would spread the contamination over empty ocean, but they couldn't eliminate the risk entirely. Freeman Dyson himself estimated that each launch would cause at least one additional cancer death somewhere on Earth. The price of reaching the stars might be measured in human lives. This wasn't just an engineering problem, it was a moral one. Was the dream of interstellar travel worth the cost in radiation exposure? Could humanity justify poisoning its own planet in the name of exploring others? The questions would soon become more than academic. Political forces were already moving that would determine whether Project Orion would fly or die. But first, the engineers had to prove their impossible machine could actually work. The proof came in fragments, scattered across test sites and classified reports. The nuclear pulse unit itself was a marvel of compact engineering. A 6-inch diameter cylinder weighing 300 pounds, packed with enough destructive force to level city blocks. Inside, an explosive charge sat nestled within a beryllium oxide channel filter, covered by a uranium radiation mirror. The entire assembly faced a flat tungsten plate that would direct the blast toward the pusher plate above. The loading mechanism was almost absurdly practical. Engineers designed it like a vending machine, literally consulting with Coca-Cola about automated dispensing systems. Picture it. Nuclear weapons dispensed like sodas, each device sliding into position with mechanical precision. The absurdity of the image couldn't hide the sophistication of the engineering. Every microsecond was choreographed. 1 microsecond after ignition, plasma and neutrons would heat the channel filler. 2 microseconds later, that energy would vaporize the tungsten propellant, creating a directed explosion that would slam into the pusher plate with calculated fury. The timing was everything. Miss by milliseconds, and the spacecraft would tear itself apart. The bombs had to be ejected through a hole in the center of the pusher plate, using what amounted to a gas gun to shoot nuclear devices into the void behind the ship. Each explosion had to occur at precisely the right distance, close enough to deliver maximum impulse, far enough to avoid incinerating the spacecraft. The margin for error was measured in fractions of seconds across distances measured in meters. Real-world testing revealed problems that no amount of theoretical calculation could predict. The shock absorber system, designed to smooth the violent nuclear impulses into steady acceleration, proved temperamental. In the gap between explosions, the pusher plate would rebound like a giant trampoline. If the next bomb failed to detonate on schedule, that rebound could rip the plate clean off the spacecraft. The engineering team had exactly 10 milliseconds to detect a misfire and compensate. 10 milliseconds to save the ship from destroying itself. Fragmentation posed another nightmare. Unlike nuclear explosions, which vaporize everything in their immediate vicinity, conventional explosives created shrapnel that could shred the pusher plate. The test flights using RDX charges worked, but they couldn't replicate the clean, debris-free explosions that nuclear devices would provide. The team was designing a spacecraft that could only be properly tested with the very weapons they weren't allowed to use. The ablation problem haunted every calculation. Each nuclear explosion would blast away a microscopic layer of the pusher plate's surface. Over thousands of detonations would the plate erode like a bar of soap. Computer models suggested the erosion would be manageable, but models weren't reality. The turbulence of rapid nuclear explosions created conditions that no laboratory could replicate. The team was essentially guessing about the survival of their most critical component. Despite these challenges, the potential remained intoxicating. The momentum-limited design promised to push the boundaries of physics itself. By using an ablation coating that would be blasted away with each explosion, The pusher plate could shed excess heat and withstand even more powerful detonations. The shock absorbers would be the limiting factor, the mechanism that transferred momentum from the blast-accelerated plate to the smoothly accelerated ship above. The numbers were staggering. A properly designed Orion spacecraft could reach 9 to 11% of the speed of light. Not the crawling velocities of chemical rockets, but relativistic speeds that would make interstellar travel possible within a human lifetime. Alpha Centauri, the nearest star system, would be just 44 years away. Mars would be a weekend trip. The outer planets would become suburbs of Earth. Carl Sagan, the astronomer who would later captivate the world with his Cosmos series, saw the deeper implications. The world's nuclear arsenals, built for destruction, could be transformed into instruments of exploration. Every warhead represented potential energy that could carry humanity to the stars. The same technology that threatened to end civilization could be the key to extending it across the galaxy. The engineering challenges seemed solvable, given time and resources. The shock absorber problem could be addressed with better materials and more sophisticated control systems. The ablation issue might be resolved through careful design and testing. Even the fragmentation concerns could be managed with proper bomb design, but there was one problem that no amount of engineering could solve: the planet below. Every nuclear explosion would release radiation into the atmosphere. The bombs were small by military standards, but they were still nuclear weapons. 800 detonations just to reach orbit, thousands more for interplanetary missions. The cumulative effect would be like conducting a nuclear war every time someone wanted to visit Mars. The team tried to minimize the impact. They designed launch trajectories over empty ocean, spreading the radioactive fallout across uninhabited waters. They calculated the cleanest possible bomb designs, reducing the long-lived isotopes that would contaminate the environment. They even considered launching from remote locations, far from populated areas, but they couldn't eliminate the risk entirely. Freeman Dyson, the brilliant physicist who had helped design the system, made a sobering calculation. Each Orion launch would likely cause one additional cancer death somewhere on Earth. The number seemed almost trivial compared to the thousands who died in traffic accidents or industrial mishaps. But it represented a fundamental moral choice. Was the dream of interstellar travel worth deliberately poisoning the planet? The calculation was disputed, criticized for its lack of supporting mathematics. But the basic principle remained sound. Nuclear explosions in the atmosphere would create radioactive fallout. That fallout would settle on crops, in water supplies, in the lungs of children playing in distant playgrounds. The cost of reaching the stars would be measured in human lives. Public opinion began to shift. The same nuclear weapons that had ended World War II now threatened to contaminate the peacetime world. Atmospheric testing was already falling out of favor as scientists began to understand the long-term effects of radiation exposure. The idea of routinely detonating hundreds of nuclear devices for space exploration seemed increasingly reckless. International pressure mounted. The Soviet Union, despite its own nuclear program, began calling for limits on atmospheric testing. Other nations, watching the fallout from American and Soviet tests drift across their borders, demanded action. The world was growing tired of nuclear explosions, regardless of their purpose. But the Orion team pressed on. They had solved the major engineering challenges. The spacecraft could work. The physics were sound. The technology existed to build interstellar ships within a decade. All they needed was permission to test their bombs in the atmosphere. All they needed was the world to accept the cost of reaching the stars. The permission never came. Political forces were already moving that would doom the project before it could truly begin. The same international tensions that had created nuclear weapons would ultimately prevent their use for exploration. The dream of nuclear pulse propulsion would collide with the reality of nuclear proliferation, and only one would survive. The end was already written. Even as the engineers continued their work, the world was about to choose between reaching for the stars and protecting the planet beneath their feet. The choice would echo through decades of space exploration, shaping every mission that followed. Project Orion stood at the crossroads of human ambition and human survival, and the crossroads was about to claim its victim. The writing was already on the wall when 1963 arrived. Behind closed doors in Washington, Moscow, and London, diplomats were crafting documents that would reshape the nuclear age. The Partial Test Ban Treaty wasn't just about weapons, it was about the future of human civilization. And that future, they had decided, didn't include nuclear bombs exploding in the atmosphere for any reason. The treaty negotiations moved with the cold precision of international law. 126 nations would eventually sign the document, including the 3 nuclear superpowers. The language was clinical, bureaucratic, almost boring. But buried within those dry paragraphs was a death sentence for Project Orion. No nuclear explosions in the atmosphere. No exceptions for scientific research. No special provisions for space exploration. Freeman Dyson watched the political machinery grind forward with growing dread. The physics worked. The engineering was sound. They had solved problems that had seemed impossible just years before. But physics couldn't overcome politics, and politics had decided that the atmosphere was off limits to nuclear fire. The team made desperate attempts to salvage their dream. What if they launched from underground? What if they moved operations to space itself, using conventional rockets to lift the Orion spacecraft beyond the atmosphere before igniting the nuclear pulse system? The modifications were possible, but they destroyed the elegant simplicity that had made the concept so appealing. Underground launches would require massive excavation projects. Space-based assembly would need infrastructure that didn't exist. More fundamentally, the modifications missed the point. The treaty wasn't just about atmospheric testing, it was about nuclear proliferation. Every Orion launch would require hundreds of nuclear devices, each one a potential weapon if it fell into the wrong hands. The same bombs that could power a spacecraft to Mars could level a city on Earth. In a world already terrified of nuclear war, the idea of mass-producing nuclear devices for civilian space travel seemed impossibly naive. The military implications were staggering. An Orion spacecraft wasn't just a transport vehicle, it was a weapons platform. The same technology that could deliver colonists to other planets could deliver nuclear warheads to enemy cities. The pusher plate system could be modified to launch nuclear weapons instead of absorbing their blast. A single Orion ship could carry enough firepower to destroy entire nations. International tensions made the concept even more dangerous. The Cold War was entering its most paranoid phase. American and Soviet forces faced each other across divided Berlin. Nuclear submarines prowled the oceans, their missile tubes loaded with city killers. The Cuban Missile Crisis had brought the world to the brink of nuclear war just months before the treaty negotiations began. In that environment, the idea of routinely launching nuclear-powered spacecraft seemed like madness. The treaty signing ceremony was held in Moscow, Washington, and London simultaneously. Diplomats praised the agreement as a step toward peace, a recognition that nuclear weapons posed dangers that transcended national boundaries. They spoke of protecting future generations from the horrors of radioactive fallout. They didn't mention the interstellar spacecraft that would never fly. Project Orion died quietly. There was no dramatic shutdown, no final test flight, no farewell ceremony. The funding simply stopped flowing. The engineers were reassigned to other projects. The test facility in California was abandoned, its launch towers left to rust in the desert sun. The dream of nuclear pulse propulsion faded like radioactive isotopes, slowly decaying into memory, but the idea refused to die completely. In the years that followed, new projects emerged from the ashes of Orion. Project Daedalus, designed by the British Interplanetary Society, proposed using nuclear fusion instead of fission bombs. The concept was cleaner, safer, but still impossibly complex. Project Longshot explored similar ideas, each iteration trying to capture the power of nuclear fire without the dangers of nuclear weapons. The closest successor was NASA's NERVA program, which developed nuclear thermal rockets. Instead of external explosions, NERVA used nuclear reactors to heat propellant, creating thrust through controlled atomic fire. The system was tested extensively, even certified for manned missions to Mars. But it too was canceled, victim of budget cuts and changing political priorities. The space program that actually emerged bore little resemblance to the nuclear-powered future that Orion had promised. Chemical rockets, the same technology that had lifted the first satellites into orbit, became the foundation for all human space exploration. The Apollo program reached the moon using carefully controlled chemical explosions, not nuclear fire. The space shuttle relied on solid rocket boosters and liquid fuel engines. Even today's most advanced spacecraft use variations of century-old chemical propulsion technology. The cost of that choice became clear over the decades that followed. Mars remained tantalizingly out of reach, requiring multi-year journeys that pushed the limits of human endurance. The outer planets became destinations for robotic probes, not human explorers. Interstellar travel remained pure science fiction, requiring generational ships or technologies that didn't exist. Contemporary space missions revealed the magnitude of what had been lost. The Voyager probes, launched in 1977, took decades to reach the outer planets. New Horizons, the fastest spacecraft ever launched, needed 9 years to reach Pluto. With conventional propulsion, a trip to Alpha Centauri would take over 70,000 years. The nearest star might as well be in another universe. The irony was bitter. The same nuclear weapons that had ended World War II and launched the space age had ultimately constrained it. The technology that could have carried humanity to the stars was locked away in missile silos and submarine tubes, too dangerous to use for exploration. The atomic age had created the tools for interstellar travel, then declared them too terrible to touch. Modern ion drives and solar sails represented attempts to work around the nuclear prohibition. These technologies promised efficient, long-duration thrust that could eventually reach high velocities. But they were weak, requiring years or decades to accelerate to meaningful speeds. What nuclear pulse propulsion could accomplish in minutes, ion drives needed decades to achieve. The physics of interstellar travel remained unforgiving. To reach other star systems within a human lifetime required either enormous amounts of energy or revolutionary breakthroughs in propulsion technology. Nuclear weapons represented the most concentrated form of energy that human civilization had ever created. By banning their use for space exploration, the world had effectively banned practical interstellar travel. Some engineers continued to study nuclear pulse propulsion in secret. Computer simulations replaced physical tests. Theoretical papers explored variations on the Orion concept. But without the ability to test real nuclear devices in realistic conditions, the research remained academic. The most promising propulsion system in human history had been reduced to a footnote in physics textbooks. The environmental movement that emerged in the 1960s and 1970s further complicated any revival of nuclear pulse propulsion. Rachel Carson's Silent Spring had awakened the world to the dangers of technological contamination. The anti-nuclear movement gained strength from accidents at 3 Mile Island and Chernobyl. Even peaceful uses of nuclear technology faced increasing skepticism and regulation. Space exploration itself began to lose public support. The moon landings had been a triumph of human ingenuity, but they had also revealed the enormous costs of space travel. The Apollo program consumed over 4% of the federal budget at its peak. The space shuttle, originally designed to make space access routine and affordable, proved expensive and dangerous. Public enthusiasm for space exploration waned as earthly problems demanded attention. The dreams of the 1950s began to seem quaint, even reckless. The confident predictions of lunar colonies and Mars expeditions gave way to more modest goals. The International Space Station represented the pinnacle of human space achievement, a remarkable feat of engineering that nonetheless remained confined to Earth orbit. The bold visions of nuclear-powered spacecraft seemed like relics of a more optimistic age, yet the fundamental physics hadn't changed. Nuclear reactions still represented the most efficient way to convert matter into energy. The energy density of nuclear fuel remained millions of times greater than chemical propellants. The basic insight that had driven Project Orion, that nuclear explosions could power spacecraft, remained as valid as ever. Modern nuclear technology had advanced far beyond the crude bombs of the 1950s. Fusion research promised clean nuclear reactions that produced minimal radioactive waste. Antimatter, though still purely theoretical, could provide even more efficient energy conversion. The tools for interstellar travel were becoming more sophisticated, not less. The question was whether humanity would ever find the courage to use them. The nuclear taboo that had killed Project Orion remained as strong as ever. The same fears that had driven the Test Ban Treaty continued to shape policy decisions. Nuclear technology remained associated with weapons and accidents, not exploration and discovery. But the stars remained unchanged, calling across the void with their ancient light. The distances that had challenged the Orion engineers still challenged their successors. The dream of interstellar travel still burned in the hearts of scientists and engineers, even if the tools to achieve it remained locked away. Project Orion had been more than just a spacecraft design. It had been a symbol of human ambition unchained. For a brief moment in history, it had seemed possible that humanity might break free from its planetary cradle and spread across the galaxy. The nuclear age had offered that possibility, then snatched it away. The legacy lived on in the margins of space exploration. Every mission to Mars carried echoes of the Orion dream. Every probe sent to the outer planets bore witness to the journeys that might have been. The nuclear fire that could have powered interstellar arcs instead remained buried in weapons bunkers, its potential unrealized. The choice made in 1963 had seemed reasonable at the time. The world had chosen safety over ambition, caution over courage. The atmosphere would remain free of nuclear explosions. The planet would be protected from radioactive contamination. Future generations would inherit a world unmarked by the fallout of interstellar dreams. But they would also inherit a world confined to a single star system, trapped by the very weapons that could have set them free. The nuclear age had promised to make humanity a spacefaring species. Instead, it had made them prisoners of their own power, too afraid of their tools to use them for their grandest purposes. The Project Orion story stood as a reminder of paths not taken, of futures that might have been. In the end, the greatest tragedy wasn't that the spacecraft had been canceled. It was that the dream itself had been abandoned. Humanity had chosen to remain earthbound, and the stars had never seemed so far away.